What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 8 Review Exercises. Let's do it. So for this question, we're meant to find the amplitude, period, and midline. So let's do that first. So the amplitude is this number in front. So the amplitude is, of course, 3. There's nothing modifying the period, and cosine typically has a period of 2 pi, so that's going to be 2 pi. And then there's a vertical shift going up by 3 out here. And that's actually coincides with the midline. So the midline is going to be y equals 3. So now let's graph it. So we're going to start by placing the midline at y equals 3. And then we've got this amplitude of 3, meaning we're going up 3 and down 3 from the midline. So I'm going to place boundaries there as well. And now there are no asymptotes per se. These are just kind of guiding lines that help us draw this. And the last thing is this little negative sign. So what does that do? That flips it. And so I'm going to show you how that works. Typically with cosine, we're starting at the high point, right on the y-axis, but that negative means we're flipping it. So now we're flipping it about this midline, and so now we're starting at the low point, okay? And now we can plot this out. And by the way, I left all this blank intentionally. It's really nice because once I know the period, then I can use that to make this work. So I'm going to make this pi, and I'm going to make this 2 pi. That's 1 period. I'm going to make this negative pi and negative 2 pi, and that's 2 periods that we can graph. And so now check it out. We're starting low, and at the end of the period, we're going to come back to low, and then in between these two low points, that's when we go high. And in between these two, that's when we go high. And then in between the high and the low, we got a midpoint on that nice midline. And now let's connect the dots. So you can see we're sort of connecting them like so. And then we got a really nice looking curve like this. And just so you can see, right, this is going up to 6, this is coming down to 0, and that's how you do it. Boom, done. So for this one, let's start with this value, which gives us the amplitude, that is 3. The period is not modified, so we're going to stick with the typical period of cosine, which is 2 pi. And then we got this, and this is a phase shift, okay? And the phase shift is going to the left by pi 6 because it's plus. If it was minus, it'd be going to the right, okay? So that's a phase shift, so it's going left by pi 6. And by the way, the midline, okay, because there's been no vertical shift or anything like that, so the midline's at the typical spot, which is at y equals 0. So let's draw these out now. So I got the midline right here in blue, and then going up and down to the amplitude of 3, right? So I'll mark this as 3, and this is negative 3. And then we got a period of 2 pi. So I'm going to do something interesting here. Like normally I'd just be like pi, 2 pi, whatever. But I've got this phase shift of pi 6. So instead of doing it every 4, I'm going to do it every 3. I'm going to make this pi and this 2 pi. This is because I want to make sure to draw 2 periods. So I got pi, 2 pi. Here I've got negative pi, negative 2 pi. So why did I do that? Because pi 6, these are now pi thirds, 2 pi thirds, right? And pi 6 is just half of pi thirds. So I'm doing this so it's easier to graph this phase shift, okay? Now we come to the fact that cosine usually starts high. So usually I would start here, but because of that phase shift, I'm shifting it back pi 6, which again is half of this negative pi third. So we're shifting it back right here. Now we can use that period of 2 pi to show that, hey, it's repeating every 2 pi. So that's going to put us again at the high point here, and then again at the high point over here, right? And then in between these points, we're going to the low point. So that's going to occur here, and that's going to occur here. And then in between these, we have the midpoints, right? So the midpoint is occurring here and here. And then the midpoint is occurring here and here on that nice midline. Now let's connect the dots. So that's how you do it. And again, just to clarify, there's no asymptotes here, right? These aren't considered asymptotes. I just draw those in to make it easier to graph, but no asymptotes. That's how you do it. Done. So for this one, we've got an amplitude of 3. We've got a midline occurring at y equals negative 4. That's because of that vertical shift down. So it's normally at 0, it's at y equals negative 4. And then we have this, which is a phase shift, okay? That's going to the right by pi over 4 because of the minus. Last but not least, the period has not been modified, so the period is still 2 pi. Okay, and you can see I kind of place these lines here. Midline at y equals negative 4, that's good to go. And then up 3 and down 3 for the amplitude. So those gives kind of like the outlines of the top and the bottom. Again, these are just to make it easier to graph. You don't need these lines. Okay, now we're talking about sine, right? Sine usually starts right here on the y-axis and on the midline, but it's going to change because of this phase shift. So let's get to that now. By the way, we're going to start to map this out. I got this is pi, this is 2 pi, and this is negative pi, negative 2 pi. This is going to allow me to do 2 nice full periods, and it's beautiful because pi fourths, pi fourths, pi, right? These are increments of pi fourths divided into 4 pieces. And that phase shift is also a nice pi fourth. So we're going to go to the right by pi fourths, and now let's start to map it out. So we see that we have a midpoint here on the midline. We're going to again have a repeat of that after 2 periods, 1, 2. And in the center, we got another midpoint here. And then now with sine, there's no minus in front or anything like that. So typically we go up, right? Halfway in between these two, then we go back down. Then in the middle of these two, we go back down and then up. And that's kind of the trajectory. So we'll do the same going to the left, going down to the min, then back up here, then back up here, and then down to the midline. So now we got 2 periods. Let's connect the dots. And so there you go. Just mark this as -1 and -7 so you can see where they end up, right? But that's the gist of it. That's the graph. By the way, again, sine, cosine, there's not going to be any actual asymptotes. So that's it. Boom, done. So for this one, we're going to start with that amplitude, which is 6. And then we've also got a midline occurring at y equals -1. That's that vertical shift down. And you can see I've already started to plot this out. And because the amplitude is 6, we're going up 6 and down 6 from that midline, right? And that's going to land us at 5 here and -7 here. Okay, now we have what's inside, but to deal with what's inside, I'm actually going to factor that coefficient out from these two. So I've got 3 times x minus, and you divide this by 3, it becomes pi over 18. Okay, so this is really helpful because now this tells me 2 things. This tells me that the period is modified by dividing the typical period of sine, which is 2 pi, by this. So the new period is now 2 pi divided by 3. And then this is the phase shift. It's going this much to the right. So it's going to the right by pi over 18. So what I'm going to do with this in terms of how I'm going to label the x-axis is I'm actually going to do it by pi ninths. Okay, pi 18ths is half of pi ninths, so it's going to make it somewhat easier to graph. So if this is pi ninths, then this is 2 pi ninths, 3 pi ninths. That's 3 pi ninths is pi thirds. And then 1, 2, 3 more, that's 6 pi ninths, which is the same as 2 pi thirds, which is the period. So that's beautiful because I can do the same going back, right? 1, 2, 3, 1, 2, 3. Here's -2 pi thirds. Now I have enough runway to do 2 periods. So now we can begin, okay? So we're starting, this is a sine function. So normally we start right here on the center and we go up like that. But instead, we're shifted to the right by pi 18. So this is pi 9, so I'm kind of in the middle. So I'm shifted to the right there, okay? And now let's use the periods. So my period is 6 spaces to the right, which means it's going to come back to the center line here. And with sine, it's actually going to hit the center in the middle of these two again. Now, in typical fashion, we're going to go up in between these two. So what's right in the middle of these two is right here, and we're going to hit that max, and we're going to come back down to the mid. Then in the middle of these two, we're going to come down, hit the min, and then go back up. And we're going to repeat this cycle to the left. We're going to go down here and then back up to the center line here, and then up here, and then back down to the center line here. And now let's connect the dots. Once again, with sine and cosine, there's no asymptote, so you don't need to worry about that. This is the final answer. Boom, done. So for this one, we're meant to determine the amplitude or stretching factor, period, midline equation, and asymptotes. All right. So the typical period for tangent, which hasn't been modified here, is just going to be pi. The stretching factor in this case is just 1 because there's no multiplier here, so we'll just say stretching factor of 1. The amplitude or stretching factor, again, it's kind of like interchangeable, right? It's what we call amplitude for sine and cosine. Here we'd say stretching factor, so whatever. And then the asymptotes. So typically the asymptotes for tangent are going to be pi halves, 3 pi halves. Basically, at every pi halves plus pi k, if that makes sense. So let me give you an example. So my asymptotes vertical are going to be here at negative pi halves, then plus pi at pi halves, and so on and so forth indefinitely. And if we want our midline equation, okay, for tangent, it's typically at y equals 0. It has been modified, sorry. So it's been dropped by 4 because of the vertical shift. So now it's going to be y equals -4. Now we have enough to kind of put this together. So again, typically tangent is going to start here right at the origin, but it's been shifting down to that midline. So we're right here. Since the stretching factor is just 1, halfway between these, the asymptote and this point, we just go 1 up and 1 down. If the stretching factor was 2, we go 2 up and 2 down, but it's not. And then we just connect the dots and kind of go up, hugging that asymptote to the right, and go down, hugging the asymptote to the left, and then we repeat. And again, to get the equation of the asymptotes, right, it's x equals, and as I mentioned, it's pi halves, that's this one in particular, and then it's going up or down by multiples of pi, so we say pi k, where k is any integer. So this is how you graph it, boom, done. So for this one, first let's identify a couple things. So first we got a stretching factor of 3. The negative is going to do something different. It's going to flip it across the midline, so we'll come back to that. Then we've got a period. Normally tangent is a period of pi, but because there's a coefficient, we divide by that coefficient. So the period is now pi fourths. And then we got a midline occurring at y equals -2 because of this -2 right here. So here's my midline at -2, and then here's the period at pi fourths. So what I'm going to do is I'm going to mark this as pi over 4 and this as -pi over 4. And then, this is a period like so. Now, typically we're starting right at the center point on this midline for our first spot, and there's no phase shift, so that's going to stay the same. And then since this is a distance of pi fourths, right, this would be -pi8 to pi8, that's the boundaries, that's where we're going to place the first set of vertical asymptotes. And then these vertical asymptotes will continue every pi fourths. Now we have all the information we need. Oh, last but not least, now we can talk about that negative, right? So typically tangent goes up and down like that, up to the right, down to the left. But because of the negative, it's flipped, okay? So now it's going to go down to the right, up to the left. And we also have to use the stretching factor, right? So typically halfway in between this point and the asymptote, I'd go down 1 if it was a stretching factor of 1. But now I go down 3. 1, 2, 3. So I go down here. And then to the left, I go up 3. And now we connect the dots. And then we'll repeat that for these periods as well. And the last thing we need is an equation for the asymptote. So I've got 1 here. Again, this is pi fourths. So I got an asymptote here at pi eighths. And then they're occurring in multiples of pi fourths. So pi fourths times k, where k is any integer. And that's how you make the graph for number 11. Boom, done. So this one we're meant to graph 2 periods, and because secant is the inverse of cosine, I'm actually going to graph cosine, and then I'm going to use that to graph the secant function. So we got 1/3 cosine x. That just means we've got an amplitude of 1/3, but the period is still standard at 2 pi, and our midline is going to be standard. It's not shifted anyway, so it's going to be set at y equals 0. So here I've got my midline, and then I've got these lines up here and down here to just kind of help us graph the tops and the bottoms, the maxes and the mins. But you might say, well, wait a minute, the amplitude is 1/3. This looks like 3, but I haven't labeled the y-axis. I can label it whatever I want. So I've done it like this so it doesn't look so scrunched together, right? I'll say that's 1/3, this is -1/3. And then my typical cosine function is that we're going to start at the top, and then we kind of go like this, right? And the period, like we said, is 2 pi. So let's make this pi, and let's make this 2 pi. And then we go to the left, -pi, -2 pi, and we can get our 2 periods. So we start at the max. We come back to the max at the end of the period, come back to the max at this period. In the middle, we're going to the min, like so. And then in between, we got the midpoints on the midline, right? Boom and boom. Now let's connect the dots. Okay, but now this is just the cosine function. We need to use this to make the secant function. So first I'm going to draw in the vertical asymptotes of secant, which are going to occur at every x-intercept. But really it's the midline intercepts, but that happens to be the x-axis, so check it out. And then what I'm going to do in purple is look at every max point, and from that max point, I'm going to draw these little upward-facing parabolas that are going to be bounded by these vertical asymptotes. And for the minimums, I'm going to do the same, except I'm going down. Last but not least, we need an equation for the asymptotes. So this one is occurring here at pi halves, and then they're repeating at every pi, right? It's kind of repeating in increments of pi. So I can say plus pi k, where k is an integer, and that's how you do it. Boom, done. So for this one, it's cosecant, which is related to sine. So I'm going to treat this as if it were 4 sine of 5x. We're going to use that to create the initial sine graph, and then take that to the next level and draw our cosecant graph. So check this out. First of all, we have an amplitude of 4. And then normally the period is 2 pi. But since we have this coefficient of 5, okay, we're going to divide by that coefficient. So now the period is 2 pi fifths. The midline is still going to be at y equals 0 because there's no vertical shift. So this is enough to start. So again, the beauty of leaving everything blank is I can label it according to this period, right? I can make this pi fifths, 2 pi fifths, that's one period, and that's another period, okay? And then I also labeled this just as is, 1, 2, 3, 4, right? And that's a nice height. It's going to give us a nice looking function. Okay, now we're talking about sine. Sine normally starts right here. Since there's no phase shift, no vertical shift, we're good to go there. And then what do, right? We go up through a quarter of the period, then another quarter we come to the midline, another quarter we go down and then back up. And then we do the same pattern to the left. So we go down, up, down. Now let's connect the dots. So here's our sine function. Now we're going to use this to build our cosecant function, which is the same numbers, constants, and everything. It's just cosecant instead of sine. So first I'm going to draw in the vertical asymptotes. Those are going to occur everywhere where the sine function is touching the midline. Now I'm going to draw the actual cosecant function. So every time I have a max, I'm going to make an upwards facing parabola within those vertical asymptotes. And at every minimum, I'm going to draw them coming down like so. And the asymptotes are occurring at multiples of pi fifths, right? So I can just say asymptotes are at x equals pi fifths times k, where k is an integer. That's how you do it. Done. So for this one, we're trying to graph cosecant, and cosecant is related to sine. So what I'm going to do is I'm going to actually start by graphing the sine function with the same constant. So we know we have an amplitude of 2/3, and then we also have a period modification. So typically the period is 2 pi, but here it's divided by that coefficient. And anything divided by 1/2 is like multiplying by 2. So we have a period of 4 pi. And then we have a midline that hasn't been modified because there's no plus value, right? Or minus value. So it's at y equals 0. So now I've labeled everything according to what's going to make this look the nicest, right? I had everything blank, so I left this as 2/3 and -2/3 because that's the amplitude, and that's going to be perfect. And then because the period is 4 pi, this gives me a period here and a period here. So now let's connect the dots. And by the way, sine always starts right here on the middle. There's no phase shift, there's no vertical shift, so we're going to leave it as is. Now we know we're going to come back to the center line at the end of the period and again in the middle of the period. And then like typical sine, we go up, down, down, up, and same going to the other side, but we'll go in reverse, down, up, down, and now let's connect the dots. So here is your sine function, but again, we need cosecant. So now we can create cosecant. So first I'm going to make the vertical asymptotes at every place where this hits the midline. Now that we have these points, I'm going to draw parabolas starting at every max point, drawing a little mini parabola going up. And again, it's going to be bounded by those vertical asymptotes. And then over here coming down like so. And then the last thing we need is our equation for these vertical asymptotes. So I see one occurring here at actually 0 and then 2 pi and then 4 pi. So they're multiples of 2 pi. So I can just say 2 pi k, where k is any integer. That's how you graph it. Done. For the following exercises, use this scenario. The population of a city has risen and fallen over a 20-year interval. It may be modeled by this, which is a sine function, and where the domain is the year since 1980, and the range is the population of the city. So this is what is the largest and smallest population the city may have. So here we see this 12,000 as our y-intercept, if you will, or so here we see 12,000 as the vertical shift, right? And that's also technically the midline. So just imagine this for a second. If we have a midline at y equals 12,000, and then we have an amplitude. Amplitude is this constant in front of the sine function. The amplitude is 8,000. So that means we go above by 8,000 and below by 8,000 for the midline, which means the smallest will be 8,000 below 12,000, which is 4,000. And then the largest is 8,000 above 12,000, which is 20,000. So there's your answers. Done. What are the amplitude, period, and phase shift for the function? So the amplitude is this constant in front of sine. So the amplitude is going to be 8,000. The period for sine is typically 2 pi, okay? But we've got a constant multiplying the x value. So we take that and we divide it by that constant of 0.628. And we do that in Desmos, we get approximately 10, so we'll say 10. And then the phase shift would exist if it was like x minus 10 or something like that, x plus something, right? But there is none of that. That does not exist. It's just an x. So the phase shift, we'll just say there's none. There's no phase shift. So that's how you do it. Done. What is the predicted population in 2007 and 2010? So years from 1980, that's 27 years, and years from 1980, that's 30 years. So we're going to plug and chug in Desmos and see what we get. So here's the value when A equals 27, right? That's in 2007. The population is 4,413. And then in 2010, when that value is 30, okay, it's 11,924, rounded to the nearest whole number. So here are your two answers. Boom, done. So for this one, we're meant to look at this graph to answer these questions. So it says at time 0, what is the displacement of the weight? And that's what's on the y-axis. So here is 0 on the x-axis, and there's the corresponding value. So it's 5, and this is in inches, so 5 inches, boom, done. So it says, what is the time required for the weight to return to its initial height of 5 inches? And here's that initial height of 5 inches. So how long does it take? Well, it comes back to 5 right here. Right? And really it says, what are they asking the period? How long does it take? Well, it looks like it goes from time 0 to 10. So since the unit is in seconds, we would say 10 seconds, boom, done. So for this one, we're asked to find arc cosine of rad 3 over 2. So I'm not going to use a calculator, but I'm going to use the unit circle. And really what this is asking is cosine of what angle is equal to rad 3 over 2. So I only see rad 3 over 2 in 2 spots for the x value. By the way, cosine matches up with the x value on the unit circle coordinates. So I see rad 3 over 2 here and here. But remember, we were taking arc cosine. So one of these is within the range of arc cosine and one is not. And the range for arc cosine is from 0 to pi. So it's in this zone. So this one is out, which means that our answer is this theta value, pi over 6, boom, done. So for this one, we're trying to find arc cosine of 1 over rad 2, which is really saying cosine of what angle is 1 over rad 2. And I've got the unit circle pulled up because we're going to use that to help us figure this out. And cosine matches up on the unit circle with these x values. Problem is, I don't see 1 over rad 2, but 1 over rad 2 simply hasn't had the denominator rationalized. So I'm going to start there, multiply by rad 2 over rad 2, and we get rad 2 over 2. And this I do see. I see it here, and I see it here. But again, we have to keep in mind what is the range of arc cosine, and that's from 0 to pi. So it's only values up here, not down here. So my only viable answer is this angle in radians, which is pi over 4. So pi over 4, boom, done. So for this one, we're starting by taking cosine of pi 6 and then taking arc sine of that value. So what is cosine of pi 6? So here's pi 6. Cosine is that corresponding x value, which is rad 3 over 2. Now we're taking arc sine of rad 3 over 2. So sine is going to give us a value from the y values of these coordinates, okay? So it's really saying sine of what theta value is going to give us rad 3 over 2, meaning where do I have rad 3 over 2 for the y value? So I have it here, and I also have it here. Those are the positive ones, right? These are negative down here, so we don't worry about those. So it's one of these two. Okay, so it's either, our answer is either this angle pi thirds or this angle 2 pi thirds. But we have to bear in mind that arc sine has a range from negative pi halves to pi halves, meaning this is out. So the only possible viable solution is pi thirds. That's how you do it. Done. So for this one, we can't use the unit circle because this value is not on the unit circle, but we can do something interesting, okay? We know that this is really saying secant of what angle is 3 over 5. And remember, secant is related to cosine, okay? So we're really saying cosine of what angle, therefore, is the reciprocal of this, which is 5 over 3. So we can start there. We could kind of make a little triangle here. This is typically how we would do it. And we'd say theta is over here, and then cosine, we know, is adjacent over hypotenuse, which means that the adjacent side is 5, and the hypotenuse is 3. But see, right away, we have an issue. And the issue is that we can't have a hypotenuse that's smaller than the leg, which means that we actually can't calculate this. We can't do this. This must be outside of the domain of arc secant, which means there's no solution. Boom, done. So for this one, we can't use the unit circle because this value does not appear in the unit circle, but I can do it a different way using a triangle, recognizing that this is really saying cosine of some angle equals 5 over 13. And then if we come back to SOHCAHTOA, we know that cosine equals adjacent over hypotenuse of an angle. So let's call this theta right here. And cosine is adjacent over hypotenuse. So I can call this side 5 and this side 13, right? It could also be 10 and 26. It doesn't have to be 5 and 13, but it doesn't matter because we just need values that work for the correct ratio, okay? Now I can use Pythagorean's theorem to solve for the missing side, right? So I can say 5 squared plus, let's call this b squared equals 13 squared. And that's 25 plus b squared equals 169. Subtract 25 from both sides, we get 144. Take the square root and we see that b equals 12, okay? Now we're taking tangent of this angle right here, okay? So I'm not even going to calculate what the angle is. It doesn't matter because tangent of this angle is opposite over adjacent. That's all we need, which is 12 over 5. And remember, you know, we're in quadrant 1 when we get this theta value. So tangent of an angle in quadrant 1 is also going to give me a positive value. So I don't have to worry about negatives, positives, whatever. So 12 over 5, boom, done. So for this one, we're going to graph using Desmos, and then we're going to explain the observations. You probably already know what's going to happen based on previous questions where I've graphed secant of x because they are related, they're inverses of each other, but let's check it out in Desmos. So what you see is secant x in green and cosine of x in blue, and you'll notice at every max point of cosine we have a parabola going up, at every min point you have a parabola going down. That's the relationship between cosine and secant. It's also the same relationship between sine and cosecant. Lastly, both of these graphs seem to be even functions, meaning they're symmetric about the y-axis. I'm going to graph both of these functions on the interval from -1 to 1, and then we're going to compare it to the graph of sine of x. So let's do that now in Desmos. So I graphed both of these with the restriction from -1 to 1, and you see, look, they both overlap each other. You can see that they're right on top of each other. Now, obviously, if we expand this out, right, there's sine, and then we expand this one out, beyond this scope, they don't overlap. It's only within this window that they seem to overlap. So hence, you know, when you cut it from -1 to 1, it is probably the exact same. So that's what I would say in that domain restricted region from -1 to 1, they definitely do appear to be the same. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.